Hi, today in the shop we're going to talk about math. Now if your index finger automatically didn't close this video, that's great. I'm going to ask you to step away from the mouse a little bit as it's going to get better. Not only are we going to talk about math, but we're going to talk about math as it pertains to hydraulics, and there's going to be a series of videos. Now, please stick with me. Don't make me do this alone. You may be asking yourself, why do I need to know math as it pertains to hydraulics when it comes to mechanicking? If something doesn't work, I fix it and life moves on. If you're an off-road guy like myself, or if you maybe in the future can be working in the off-road, if you work on general pieces of equipment, older pieces of equipment, there will come a time where you're gonna basically have to use this math. So I'm gonna walk you through it. We're gonna do an example. I use it actually quite a bit in my career. It's helped me a lot. And I'll give you an example. We'll go through it together. I'll try to make it as interesting as I can. And if it's not interesting, at least I hope you find it informative. A place where you may use this information is if you work in a dealership. So sometimes engineers mess up and they design a machine wrong and the hydraulics just don't work properly, and you may actually have to design and come up with we'll say a field fix until they can come up with a product repair in the future. More than likely, you'll use this information a lot when diagnosing or installing attachments or implements onto an existing machine. And that's what we're going to talk about today, is we're going to either diagnose or install an implement on an existing machine. A lot of implements, they're installed and they just don't work maybe as well as they should or as efficiently they should, and a lot of owner operators and just their operators themselves struggle with this equipment day in and day out. They just get used to it even though it may not be right, and you come along and you make it better. Don't cost a lot of money and you look like a hero. So let's go ahead and we'll start on that, and we'll see what we can do. I'll meet you at the machine. Okay, so what we're going to do is I want to install a grapple on this old 530 case rubber tired loader, or backhoe as it's sometimes known. I've always wanted a grapple on this thing, and I think we should design one and install it. So first off, for those of you, let's talk about what a grapple is. Okay, so I got my tractor, the loader, and the bucket, and I need to put a grapple on it. And a grapple kind of does what its name implies. It grapples with things. So we'll put a little hinge here. We'll have to weld a hinge on, and we'll have the grapple come down so it can grab things in the bucket. As well, we need to be able to put things inside, so we need to be able to lift the grapple up. So I'll put a little weld on here and a little eye on here, and we will hook a hydraulic cylinder in between. And now we will be able to raise and lower the grapple. So this is a hydraulic section that isn't standard on the machine. We need to install this cylinder or cylinders. We might have to have more than one. And we need to plumb it into the existing machine hydraulics. Now we have a choice to make. We can either build our grapple from scratch and build our cylinders and put it in here, or we could call an implement manufacturer like Welco, Beals, or Craig, for example, and say, we need a grapple kit for a 1966 case 530 rubber tired loader, and you will probably hear crickets on the other end of the line. So they of course won't make one for this machine, and a lot of implements just simply don't fit every machine out there. They build their implements to fit the average machine. So they will probably tell you that, yeah, we got a couple of grapples. We've got a grapple that'll fit a wheel loader with this size of bucket, or we got a grapple that can fit a skid steer with this size of bucket. And if we bought them, welded them on, the grapple would go up and down and they would work. Now, would they work 100%? Likely no. And that's where we'd come into, as the welder puts this all in, we plumb it, and then the operators and owners are not very happy with the speed and the force of our grapple. So let's talk about that, speed and force. Speed is, well, again, how fast the grapple goes up and down. Actually very important to the operators for timing of grabbing things, for being able to drop open the grapple in time to drop things or grab them before they drop. Speed is incredibly important to operators. So if this grapple opens and closes a half a second too slow or too fast, the operator is not going to be very happy. And a half a second doesn't seem like very long, but they will complain about it. The next part of that, the next component is force. Okay, so how strong the grapple is. If we have a grapple that's too strong, we crush and break everything we try to grab. We can't grab anything gently. We may even overpower the bucket or physically rip the bucket apart. If it's too weak, the grapple's not strong enough, can't hold what we need, and we drop our load. So if we put on a wheel loader grapple, it may be too strong for this bucket. If we put on a skid steer grapple, it may not be strong enough, and the speeds of those two machines may be not ideal. So we have a few components to talk about. Force, and the second component is speed, and the third one, which ties into these two later on, that's not quite as important but does make a difference, is power. Force, speed, power. Okay, so force, how strong it is, speed, how fast it moves, and power is how much time that takes. So the more power we have, the more force and more speed we can get. But let's worry about the first two. And this video, we're just going to concentrate on the easiest one to figure out, which is force. So let's go back to the drawing board and we're going to talk about force for a while. Okay, because I'm cheap, I'm not going to go to any of the manufacturers and buy myself a grapple kit. I am going to build it from scratch. So I'm going to go get a grapple or build one somewhere, like an auction sale, or just build one out of some steel I got lying around. I'm going to put a hydraulic cylinder on there because hydraulics are nice and handy compared to having cables or winches or some other mechanical means. And I'm going to tie the hydraulics into the backhoe's existing hydraulics. So I've done a little bit of research, looked it up, and the hydraulic system of the backhoe puts out 25 gallons a minute, and it is the main relief setting is 3000 psi on the loader. So this is what I've got to work with, my hydraulics on the tractor that have already been engineered and designed there, and I want my grapple to play nice with the rest of the system. So I've got some old cylinders lying around. I'm going to go grab one and we're going to see if it works. Okay, so there's my cylinder. It's the right color and it's free, so I kind of want to use it. So now, to figure out how much force that this cylinder can put out and see if it's going to work for me, I need to take it apart and measure the size of the piston. So I'm going to head off and do that. Okay, so I went and took the cylinder apart and I measured the diameter of the piston right in there, and it is 3 inches right on the money. So I like metric, but when it comes to figuring out our force, I find imperial a lot easier to deal with. So we're going to make this video about imperial, and I'll do another video showing this same thing yet in metric. So this first series will be in imperial. So I need to know some things. I need to know some formulas. So we need this formula that we need to remember is force is equal to pressure times area. Easy enough. Okay, now the force is in pounds. Okay, so just simply a pounds. Pressure, if we're talking imperial, is in psi, or pounds per square inch, or pounds per inch squared, times the area, which is in inches squared. So now that we got this formula, I think what it might be, the easiest way to solve our problem, is let's figure out how much force this one cylinder will put out. If we remember our specs from our existing hydraulic system in our backhoe, if I remember right, I said it was 25 gallons per minute. And the pressure was 3,000 psi on the main relief. And when we were designing a system, we had those two things we needed to talk about, which was force and speed. These two numbers deal with those two things. Force is with psi. Speed has to do with the amount of oil in given per minute. So this one here, we're talking about, this video is going to deal with force, so we care about this number. We don't care about the speed at all at this time. So let's put this number into our equation. We need to know how much force this cylinder is going to put out. So we need to know how many pounds of force equals psi 3,000 times inches squared. Now, the area. So if I put 3,000 psi in this cylinder, it's going to push on the piston, pushing it out. So that's going to be the area I need to figure out. The piston is round, and there's the center of it. So I need to figure out how much area this is. So let's do that. Okay, so I said my piston was 3 inches in diameter. So I need to figure out how many square inches fit into this 3-inch diameter circle. There's two ways we can do that. If you're old school like myself, you'll remember this formula from school. Area equals pi r squared. Now, we're going to do this both ways. Area equals pi r squared. So we need to know what pi is. Pi is 3.1416, or you just look it up on your phone. R squared, R stands for radius. So this is diameter. So that means from the center of the circle out is radius. So I just take the diameter and divide it by 2. That equals 1.5 inches. So 3.146 times 1.5, and it's squared, so the radius times the radius again, times 1.5. Okay, let's figure that out. So 3.1416 times 1.5 times 1.5 equals 7.068 inches. Now this is 1.5 inches times 1.5 inches, so inches times inches is inches two'd or squared. That is the area of my circle. Now there is a different way to figure this out as well. I know my diameter is 3 inches. And if I go and make a square around this, that's supposed to be square. Okay? So I know this is 3 inches and this way is 3 inches. Somebody figured out that the area of this is just over 3/4 of the entire square. So if I got rid of all of these little chunks over here, this area left over is 0.7854, so just over 3/4 of that entire squared area. So if I remember this number, if I go 0.7854 times diameter squared, it should give me the same answer as this. So let's try it out. 0.7854 times the diameter, which is 3 inches, times the diameter again, another 3 inches. So 0.7854 times 3 equals 7.068. So 3 times 3, that's inches two'd. So we came up with the exact same number. So it doesn't matter which way you like, if you prefer this 0.7844 times diameter squared, or you prefer this pi, we come up with the same answer. So let's go back to our original equation. I'm going to keep the number on the board. So our force equals, if we remember right, our pressure was 3,000 pounds per inch squared times our area, 7.068 inches squared. So we multiply those together. 3,000 times 7.068 equals 21,204. So we got pounds divided by inches squared times inches. So those cross out, we're left over with just pounds. So 21,204 pounds of force our cylinder will put out with the current loader's hydraulic system. Now we get to decide, is this enough? Is it too much? Or is it too little? Let's say, oh geez, I actually need about twice that amount of force. I think I need about 40,000 pounds. Well, let's just add 2 cylinders to our grapple, and voila, we are now at 42,000 pounds. Ideal. If we decide this 20,000 is too much and we need, let's say, half of that, there's 2 things we can do. We could cut the pressure in half, that would drop that in half, or we could make our cylinder, instead of a 3-inch, we could make it something half the size. So we can make something with 3.5 inches squared area. And that would give us, again, half the force. So it's a balancing act between the amount of pressure in the hydraulic system and the amount of area of our actuator, which in this case is a cylinder. So I'd like you to figure out how much force does this cylinder exert when there's 5,000 psi of oil pressure inside of it. I'm going to give you a few minutes to figure it out, so just pause the video, figure it out, and then we'll see if we're right. Okay, did you come up with 141,000 and change pounds of force? If you did, that's what I got as well. This is a typical cylinder on an excavator, and that is a typical force number to be exerted on said cylinder. So if you didn't get this number, let's go through it and see maybe where we might have went wrong. So our force equals pressure, which we know is 5,000 psi, times the area, which we need to figure out of the cylinder. So area equals, most mechanics like to figure it out, the square and the percentage of it, that's 7,854. So let's do it that way. So area equals 0.7854 times diameter squared. So if I put that in my formula, I'll try to do that a little neater. 0.7854 times 6 times 6, because that's the diameter of our piston. So 5,000 times 0.7854 times 6 times 6 equals that, 141,372 pounds. For bonus marks, What does the hydraulic pressure, there's my little gauge, what does my hydraulic pressure need to be for this cylinder to put out 80,000 pounds of force? How much pressure do I need? So same 6-inch cylinder, we don't know what the pressure is for that cylinder to put out 80,000 pounds. Let's manipulate this formula and see if we can do it. Okay, so now the question is, how do you manipulate a formula? Again, there's two different ways we can do it. There's the old school way. Force equals pressure times area. Doesn't matter which way we do this. This is an old school way. I'm going to show you both ways. We know the force, 80,000 pounds. We know the area because, well, we did the math before. So we know those two numbers. We don't know the pressure. So if you have an unknown here, we need to get all the knowns on the same side of the equal sign. So I need to move this A over to here. So easiest way to do it is, well, I wouldn't say the easiest way to do it, but doing it this way, manipulating formulas, whatever happens on this side, the equal sign, the opposite has to happen over here. So this is times area. So if I need to move the area over to the force side, instead of multiplying, I need to divide. So it would be force divided by area equals pressure. So if I took that 80,000 pounds, divided it by the area of the cylinder, I would get the pressure in the cylinder. There's another way to do it. What I find is a little easier, is just make yourself a triangle. Inside the triangle, I split it into 3 quadrants. On the top, I'm going to put force, P for pressure, A for area. This is super easy to figure out as long as you can remember this. I know the force, I know the area, I do not know the pressure. All I got to do is cover up the P, and the formula is force divided by area, which is what we said happened right here. If I want to know what the area is, I just cover up the A, and it's force divided by the pressure will tell me the area of the cylinder. According to our very first example, we wanted to know what the force is, so I cover it up, and it is pressure times area. So back to our original question here of how much pressure we need. Okay, so I'm going to cover up the P for pressure, and that leaves me force divided by area. My force is 80,000 pounds, so 80,000 divided by, and I need to know what my area is, so I'm going to put in my area formula, 0.7854 times 6 times 6, and the pressure is equal to 2,829 psi. I'm going to end the video here as this has gone on way longer than I intended, and it's starting to feel like cruel and unusual punishment. I hope I didn't cause any of you serious or permanent injuries. Take a break, and when you feel strong enough, come back and check out the second video in the series. I promise it will be much, much shorter. Thanks for watching.